We're going to start this session a bit late just because people had trouble coming here, and there'll probably be some people joining us, but we'll start now. This is a very special session, and it follows on a whole series that we've been having. As you know, it's about the Bible and Genesis, and this one is called For Dust Thou Art, and Unto Dust Thou Shalt Return. And what's interesting about this, our panel today, is their various backgrounds. I'll read them as they're speaking, but it's a real treat when you go, A, to speak to them personally, or B, to know how they're putting it all together. I think it's a phenomenal presentation, and allowing you to look at biblical origins or our origins as a people from different perspectives. So I'm going to start off with, I'll describe our first speaker, and I'm going to be limiting their bios, because if I read all of their bios, we wouldn't have time for anything else. So Tsvi Piran, he's a associate professor. He's not associate, he's a full professor at Hebrew University. He's the professor for Schwartzman University Chair at Hebrew University. His background is he has a BSc cum laude from Tel Aviv University, MSc cum laude from Tel Aviv University, and PhD from Hebrew University. Now, some of the things he's done that are going to be interesting for the talk is he's been a visiting professor for physics at Columbia University, physics. He's been a visiting professor for astronomy, I'll repeat, astronomy at Harvard University. And then he was dean of the business school for the past 5 years. Now, he fortunately got a good grant, and he's been forced back to do physics. So with that, we're going to start off with Professor Tsvi Piran.
Thank you. We just arrange this. Okay. The Chinese Emperor Rengzong was one of the strongest emperors in China. He lived around the year 1000. And on April 30th, on April 30th, he ruled the Northern Song Empire for over 40 years. And one day, it was April 30th, it was written here in the wrong number, it wasn't 1063, it was 1054. He got up in the morning, he woke up in the morning, and he was very upset. Sorry, it was July 4th, I'm sorry. I was expecting to speak with hello? Okay. So he woke up, and he was very upset. So why would the Chinese emperor be very upset? He saw the sun, but in addition to the sun, in the broad daylight, he saw another star, a very bright star, much brighter than Venus. Sometimes you can barely see in the early morning, but this was midday, and another stars appear in the sky. And to him, this was considered interrupted as a very bad omen. This was a sign to him from the skies that he is the sun and somebody else is going to replace him. He was extremely upset. The star was called the guest star. This is the Chinese record describing the guest star. This was written by the Chinese royal astronomer. This is the Chinese name of the royal astronomer. The name was not really the royal astronomer. This astronomer was called the governor of the sky kingdom. So the Chinese emperor believed that he is not only the emperor of the land, the sky also belonged to him, and there was a special governor that was responsible to the sky. This was this royal astronomer, and he was charged with keeping the stability of the heaven. And this governor of the sky was in deep trouble, because this is definitely not keeping the stability of heaven. Something happens there unexpected, unwanted, unneeded. So this is the continuation of this story, what was going on. And in short, the sky was observed during daylight for 23 days. For 23 days, you could see the sky in broad daylight. Then it gradually was dimmer and dimmer, but it still could be seen for about a year later during the nighttime. Now, this royal astronomer, his name was not certain, but some researchers claimed that it was Q-Sed-Jiang, had a very unfortunate fate. The emperor was unhappy with this bad news, and the poor guy lost his head. It's not clear what was exactly the excuse, whether because he didn't keep his job properly to avoid keeping the stability of the sun, of the sky, or because it was keeping secrecy. This was another option, which is not clear, is that everybody who knew too much about this guest star, his head was lost his head, so to keep this whole thing secret, everybody saw it. Now, everybody saw it. This was an Indian engraving from the same time, and you see the two suns in the sky. This is dated exactly to the same time. There is one record from Europe. Apparently, a Pope, Leo, died a couple of weeks later, and this was interpreted by this monk, this guy, Terracus de Exlasias Petri. So this guy interpreted this as the Pope was, Leo was so important that God sends him to heaven accompanied by a star. So this was also seen in Europe. This is the only record. It was also recorded by Islamic observers. And this is historic record of other guest stars. You see, we have records from about 2,000 years ago. Until now, we have seen other events like this. We've also seen such event, very bright event, recently, just slightly more than 20 years ago. This guy is Ian Shelton. He was actually technical assistant in one of the largest telescopes in South America. He finished his duty. He goes out of the telescope in the morning. He looks in the sky, and he sees something strange. It was not daylight. This case, it could not be seen by daylight. It was just the sun was just barely rising before a few minutes before sunrise, and he realized that there is a new star in the sky. He rushes to immediately understand that this is another guest star like this. He rushes to take pictures of it, and this makes the news of immediately the next day. It's in the headline in the New York Times, and the phenomena is called the supernova, and it was a very excited time for all of us. So, what is going? This is the supernova of 87A. This is the year. A is just a number. We have it A, B, C, D according to the number of appearance. So this was the first one which appeared this year, and this is the region of the sky before, and this is the region in the sky when the supernova is exploding. This is a focus on the supernova. This is how this region is seen today. Something very strange is going on there. Now, all this event that I showed you here happened relatively near to us, in our galaxy, or just very next to our galaxy, but we actually see such events all the time. This is a very distant galaxy, just like our Milky Way. The structure that we see here contains about 100 billion stars. And this is a supernova exploding in this galaxy. It's difficult to compare the light from here to there, but if you do a careful calculation, you see that the light from here is as much as the light from these 10 billion galaxies together. So for a short time, for about a month or 2 months, a single star, which we call a supernova, is shining as much as 100 billion other stars. And this is why when this was near to us, it was so bright that we could see it in daylight. What is happening there? Usually, a regular star like the sun, there is a pressure, there is a balance between two giant forces. There is the gravitational pull of the star that pulls it inwards. The star wants to shrink again because of its own gravitational force, and this is balanced by pressure. And the pressure is because to get the pressure, the center is extremely hot, getting up to something like 10 million degrees. So there is a very hot center, making the gas of the star extremely hot and the pressure extremely large. And this compensates for the gravitational attraction, and there is a balance. Now, to maintain this heat at the center of the star, the star has to work. And to produce this heat, the sun or other stars really burn hydrogen to helium, just like what is happening in a H-bomb. Hydrogen is continuously converted into helium in the centers of stars, and on Earth, the same process, as I said, is what makes H-bombs explode so violently. Now, in a sentence which is not related to the rest of the talk, I will say that we are trying to do this in a controlled way, not in explosion, as an explosion on Earth, because if we manage to convert hydrogen to helium, this will give us an everlasting source of energy which will relieve Earth from all energy problems. There is enough helium to last, enough hydrogen on Earth to last forever. In my mind, this is probably the most important challenge facing humanity, to do this in a controlled way. And this is an experiment, a huge experiment trying to do such things. We have not reached this stage yet, but we are slowly getting to this achievement. Now, back to stars. The stars have energy crisis, will have eventually energy crisis, because if you're burning hydrogen at certain rate, at one day, this hydrogen will be finished. And once the hydrogen will be finished, the star cannot burn it anymore because there will be no energy supply, just like an energy crisis that could happen on Earth when we run out of fuel. And in this case, the star begins to behave differently. It cannot go on like a regular star. The first thing that happens, the star expands and becomes a giant star. So if we think about it, if this is our sun, in about 5 billion years from now, the sun will expand and it will be so large that it will engulf the Earth. So it will be something which we call a red giant, and the whole Earth will be swirling within this red giant. Of course, no one could live in such a situation. This will happen in about 5 billion years from now, so we don't have to worry about it so much. So if we have a small star, the sun is a relatively small star. A small star like us will eventually, after expanding to become a giant, will shrink down and become what we call a white dwarf. There's too much light here, so you cannot see. This is the brightest star in the sky. It's called Sirius. Now, Sirius has a companion. This small dot here is a companion of Sirius. Is it possible to dim the light? אפשר להחשיך את האור באולם? So this small speck of light here is not a problem with the picture. It's a real star. It's a very tiny star. But it contains as much mass, almost as much mass as this huge star, as this, the main star Sirius. You can barely see it now. Now, this star is so dense that to have an idea what's going on here, if you take a teaspoon of the material of the star, this teaspoon will weigh just like one elephant. In other words, it will be about 1 ton per teaspoon. This is just to give you an idea how dense is this material, and the whole star is very small. This is why it's called the dwarf star, and this is what will happen to the sun. Larger stars explode as a supernova, and this is what the Chinese emperor saw, and this was E.L. Shendon saw, and this is the really much more exciting. In a supernova, this is some cartoon of what's happening in a supernova. We have a star here, and the star explodes, the whole star explodes, and the center collapses to what we call a neutron star, and the surrounding material is ejected to the outer space, and then it floats in the outer space for years and years. This is a distant supernova in a distant galaxy. Now, the core of the star collapses and becomes a neutron star. And the hot envelope, which is ejected to the outer space, is called a supernova, and this is what we all see. Now, just to think about a neutron star, I mentioned before that a teaspoon of a white dwarf weighs like an elephant. A teaspoon of a neutron star material weighs like 100 million elephants. So if you want to think about it, take all the people of the United States, about 300 million people, the mass of them can be, in a neutron star will be shrunk to 1 teaspoon. This is how dense is a neutron star. The whole size of a neutron star, which contains as much mass as the sun, is about 10 to 20 kilometers. So this is a very strange object. And in fact, even so it was suggested as early as 1932, many astronomers did not believe that such strange objects can exist in nature. Now, this is the supernova that the Chinese emperor saw 100,000 years later. This is the material which was ejected from the supernova. In the explosion, the core becomes a neutron star. The envelope, the rest of the star, is ejected to the outer space, and this material which is ejected to the outer space is floating in the space for many years, for hundreds, thousands of years, and this is how we see it. This is the center of this region, and we can see the neutron star here at the center. And this is a calculation of how supernova happen, how the explosion happens, that takes place, that was done here at the Hebrew University by Eli Livne, but that's another story. And we see here the material collapsing to the neutron star, which is forming here, and at the same time, this is, you can see here how the explosion is beginning, and in a second it will all explode and puff up, and this is when the envelope will be ejected. How do we know? One way that we know it is that a huge pulse of neutrino, a strange type of massless particles, is ejected to the outer space at the time that the neutron star is formed. Now, this supernova, the 87A, exploded in 27th of February, 87. I was at Princeton at the time, and actually on March 2nd in 87, we predicted that detectors like this one, this is a Japanese detector, will observe on Earth about few dozens of neutrinos coming from the supernova. So this was a very quick calculation that we did, and then we knew that this detector would supposed to see them. Then there was a competition between Federal Express and the Yamata company, which is the equivalent of Federal Express. Because I remember rushing down to Federal Express in Trenton just to catch the 5 p.m. Shipment to get the paper to Nature, and this paper was published on March 12, 87. I didn't know at the time, but this detector was built on a high mountain in Japan. There was no direct communication to this mountain, to this detector. So the way they got the data is they sent a graduate student with a backpack full of magnetic tapes. This was 87, so we were using huge magnetic tape. So this graduate student was going with a backpack, was actually hiking for about 10 kilometers with this huge backpack, and they didn't realize actually that the supernova took place. They didn't know, were not aware of it. So they were sending down, there was a grocery store, which was a deposit place for this Yamata shipment, and they deposited these magnetic tapes with this very important data of these neutrinos down there. And it took actually, since they did know that it was urgent, they were not aware of the time that there is this data of the supernova that they have recorded, so they sent it by regular mail, and it arrived Tokyo only after a week. So later on, a few weeks later, the Japanese came out with this confirmation, the observation of these neutrinos, and Koshiba, who was the main person beyond this experiment, actually received a Nobel Prize for this discovery. Okay, so small stars die, becomes white dwarf, larger ones become neutron stars, even larger one becomes a black hole. This is a really exciting story because in some cases this will emit something which we call a gamma ray burst, a very energetic pulse of radiation, and which can be seen only by satellites. This was detected by coincidence by the Americans have sent a defense satellite to space, not intending to make scientific discoveries, and to their great surprise, they saw flashes of gamma rays coming from space. It took us a long time to figure out what is going on. By now we know that these bursts are associated with events in which black holes are formed. So, there is astronomer general warning. A nearby gamma ray burst can be dangerous for your health. There is a claim that the dinosaurs were killed by smoking, but there is a larger chance that they were killed by a nearby gamma ray burst. So in some communities, gamma ray bursts are called the star of doom, or doom star, and this is a nearby star called Eta Carina, which some people speculate may explode every day and produce a gamma ray burst which may be unpleasant to us on Earth. That's why we have to watch out, not that we can do something. If this explodes and it's really dangerous, there is nothing we can do. But dying stars have much more important role, and this is really what I wanted to tell you in this whole talk. We, as humans, are made mostly of oxygen, hydrogen, and carbon. The Earth is made mostly of oxygen, silicon, calcium, and iron, and also many other metals, something more valuable like gold and silver, and some less valuable. So there is a whole enormous variety of elements that we have around us on Earth. However, if you recall some of the earlier discussions, the early universe provides us only with hydrogen and helium. Where do all these other metals come from? Where the materials come from? Where does the oxygen, carbon, silicon, calcium, and iron come from? The only place in nature that these elements can be synthesized is deep inside stars. I mentioned before that star, like a sun, burns helium to hydrogen. It doesn't end there. Sometimes, not in our sun, the hydrogen is burning to helium. Sometimes, not in our star, the helium will continue burning and produce carbon. And sometimes, if the star is massive enough, the carbon will continue burning and produce oxygen, and so on. This oxygen will produce silicon, and silicon will eventually produce iron. So the whole list of materials which are synthesized inside stars. But it's not what's good for us if this is happening inside stars. If it's inside the star, how can we use it? How can we make out of it if it's inside the star? And this is the role of supernovas. Because eventually, the heavy stars explode. This explosion sends a very large amount of material to the outer space. And this material which was ejected to the outer space condensate into clouds. And in these clouds, this is a very famous picture from the Space Telescope, which everybody saw and admires the beauty. But what is really beyond this picture is that this is a region in which new stars are formed from clouds of gas. But this gas is not pristine gas. It's not the original gas that was created in the Big Bang. It is synthesized gas that was once inside other stars, was synthesized inside stars, And this gas here that we see here contains all these heavier elements, contains carbon, oxygen, and so on. So this is really like a phoenix, which is coming back out of its ashes. So the story is that we have a star, the star atoms are synthesized inside the star, then the star explodes as a supernova. The material is ejected to the outer space, forms clouds, and the clouds condensate to new stars, and from this material, the sun and our whole solar system and us also were created. So this is really the end of my talk. We are all made out of stardust. And it may please you to know that all your atoms were once inside stars, and without a star doing this, all of us would not have been able to be here. Thank you.
Thank you, Professor Piran. That was very, very topical with our, from dust thou art. You can see how we really are from dust. Thank you very much. And our next speaker, you could see how we're sort of going from various forms, which is why it makes this so interesting. Our next speaker is Professor Ronnie Ellenblum. Now, he comes from a totally different perspective. His BSc is in geology from Hebrew University, MA from geography, historical geography, Hebrew University, and PhD, historical geography at Hebrew University. Part of his trip, he did a postdoc at the Sorbonne. Presently, he's an associated professor at historical geography. I could never figure out what that is, but we'll find out. And he's also, among other things, a life fellow at Cambridge, in Cambridge University in England. He presently, his scientific initiative is direction of the Vadam Jacob Archaeological project. So you see here we have a whole range of background, which leads to a very interesting process. So welcome, Professor Ellenblum.
Tsvi Piran gave me a rare opportunity to start from his own lecture and to continue from the stars to what happened in the Earth, in the 11th century. He spoke about a supernova, the supernova of 1054, which is exactly the period I'm going to speak about in this lecture, explaining the omen that was seen by the Chinese at the time, kind of explaining the omen. I will tell you a story that, so I think, was never told before as such. I will start from the story itself, and then I will go into the details, into the aspects of this story. This story, in short, occurred during the 11th century AD in this region of the world, in the East Mediterranean, During this period, between 950 and 1072, there were several lingering climatic disasters which were limited only to the eastern side of the Mediterranean. They were not felt in Europe of the time. They were felt as far as you go to the east, all through the eastern Mediterranean. There were several consecutive crises or disasters. The disasters can be divided into three. In the south, there was a long series of droughts in the Nile. The Nile did not rise for many consecutive years. Several of these disasters were of biblical dimensions, of 4, 5, 6, and 7 consecutive years in which the Nile did not rise. If the Nile does not rise, there is a famine in Egypt, people are dying, and usually we know about it. So I will give you the details later, but between 950 and 1072, there was a very unusual series of droughts in Egypt. At the same time, and especially during the mid-11th century AD, there were a series of droughts in Palestine, Syria, and Jordan. Very unusual and very long and very fearful series of droughts. At about the same time, not always the same year, but during this period, between 950 and 1072, there were, again, series of very lingering and very strong cold spells in the northern part of the eastern Middle East. When I speak about the northern part of the eastern Middle East, I speak about a region that extends from the steppes from Samarkand and Bukhara, and north of the Oxus, along the northern part of the Caspian Sea, up to the Danube. And when I speak about extreme cold spells, I speak about very unusual events. I will give you several examples later, but I will start for them right now. Consecutive years in which the Tigris and the Euphrates in Baghdad were solidly frozen. And in the same year, we read in a totally different sources about the Danube and about the Oxus being solidly frozen. These are things that we don't read ever after. About days of snow in Baghdad, weeks of snow in Baghdad, about the Danube being frozen, and about the Oxus. And all these events occurred at about the same year, 1027, 1028, 1029, 1032, 1033, 1038, 1043. In a very short period of time, we are talking about a cold that caused famine and pestilence in the northern part of the eastern Mediterranean. The result of this concurrence of dramatic events, the results were the abandonment of cities because of the pestilence, because of the hunger, because of the famine, and because of the desertion of strong populations, and a very unusual and very strong wave of dislocation of pastoralists who used to live either in the north or along the sedentary regions in the center and south, and were forced to abandon their way of life or to abandon their economical niche and to go elsewhere to look for pastures, for fodder, and for food for the pastoralists themselves. I will just mention some of these events of nomadizations or dislocations of pastoralists from the north. Probably the best known of them all is the wave of a group of tribes known as the August Turks, the Rus, from the steppe, who came, the most known part of them is known as the Seljuks. The Seljuks started arriving in 1027, 1028, 1029. They cross the Oxus, not far from Bukhara. Within about 20 years, in a domino effect, they actually destroyed Iran, plundering and destroying city after city, after Iran was, practically speaking, ruined. And then they entered Mesopotamia. You can see Baghdad and Basra. And they continued plundering and destroying the Jazeera, Armenia, entering Asia Minor. Between 1027 and 1047, it's the main wave, but it's up to 1058. At the same time, at exactly the same time, from a totally different part, but it's the same wave and of the same reason, we read in the Greek chronicles of Byzantium, we read about waves of nomads invading the Byzantine Empire, defeating the only regular army of the world at the time, or of the Western world at the time, the Byzantine army, both the Western army, the Eastern army, and both of them combined, forcing the Byzantine Empire to pay tribute to nomads. One of the groups of the nomads was called the Pechenegs, Patzinaks in the Greek sources, and the other one was called Uzes. As I told you before, the Turkish tribes that invaded the Eastern Mediterranean, especially between 1040s and the mid-1050s, were the August Turks, the Rus. Uzes is the Greek way to pronounce the same name, the August Turks. So we can see that at the same time, culminating between 1050 to 1055, there was a series of domino effect of nomads invading and plundering the northeastern Mediterranean. Among the effects of this dislocation, of this nomadization, we can point at the replacement, or the collapse, or the deterioration, or the crumbling. You choose the word, because the word collapse is very is not very exact. But Constantinople, the Macedonian dynasty that ruled in Constantinople for almost 200 of years, crumbled and was replaced by the Komneni and the Dukas, but mainly by the Komneni, who rose to power when the disaster was abated. In Baghdad, until 1055, there was a dynasty that ruled vis-à-vis the caliphs of Baghdad, the Buyids. The Buyids crumbled, disappeared, collapsed, and replaced by a nomadic state of the Seljuks when the disaster was abated. In Egypt, in the earlier phase of this ecological or climatological disaster, in Egypt, in the earlier phase, the Irshidid dynasty collapsed during the first phase between one of the droughts of the late 10th century, between 963 to 969, 963 to 969. At the end of this period of famine and hunger, the government was not able to rule the country anymore and was replaced by a different dynasty that invaded the country at the time. Muslim chroniclers who describe this period are talking about the destruction of Fustat, the city of Fustat, the ancient capital city of Egypt that was built by the first Muslim rulers of Egypt, was actually destroyed and replaced during this period by a new city, the city of Cairo. So we are talking about the destruction, abandonment, and change in Baghdad. Destruction in Fustat. We are talking about a different story that I don't think I will be able to enter in this popular and short introduction. The destruction and abandonment of Kairouan. We are talking about replacement. We are talking about replacement of dynasties and by collapse of bureaucracies such as the Byzantine, the Mesopotamian, the Egyptian, and many others. We are talking about, if I have time, I can give the texts that are describing the sack of libraries and the collapse and unexplained collapse of centers of learning. I will just suffice myself, because living in Jerusalem, to give one example. There were two centers of Jewish learning, or the Jewish learning in the East. The Jewish academies in the East disappeared without any reasonable explanation during this period. The Jewish Academy of Sura and Pumbedita, which were long before were established in Baghdad, disappeared in 1038 during this period of disaster. The Jewish Academy, the Yeshiva of Jerusalem, disappeared also in the late 1050s or 1060s, when Jerusalem was suffered from hunger, disease, and so on and so forth. But just to give you some theoretical background to what I'm talking about, I will just a second. The traditional approaches to the history of our country, of Palestine, in the early Muslim period, can be summarized very briefly in 4 points. The idea that I studied when I was a student, is that the Islamic conquest of the Eastern and Southern Mediterranean marks the end of classical urbanism and the actual urbanism of the medieval period, not only here, but elsewhere in the Mediterranean. The basic idea, the basic belief that I was taught is that cities and villages rapidly declined and were deserted, becoming Middle Eastern or Islamic cities. Some scholars asserted that many cities continued to exist until the mid-8th century, declining because of an earthquake that occurred later, but not later than the 8th century. The most advanced ideas raised by the British Hugh Kennedy in the mid-1980s was that the classical antiquity in the Middle East, the decline of the classical antiquity began in the 6th century before the arrival of the Muslims, and that it lasted for half a millennium. Kennedy and his followers did not blame Islam for the decline, But nevertheless, he believed that there was a decline between the arrival of Islam and the arrival of the Crusades in the late 11th century. All those ideas, when we look for the origin of these ideas, we will go back to the 19th century, to one great Belgian scholar, Henri Piran, who lived between 1862 to 1935. He wrote several books. The most known among them is The Medieval Cities in Muhammad and Charlemagne. He, in a series of articles he published in the Revue Historique in 1893, 1897, he asserted that the Muslims, he asserted that actually the Middle Ages started when the Mediterranean was divided between Muslims in the south and Europeans in the north. Before him, the basic idea was that the Middle Ages started earlier because of the invention of the Germans. Henri Piran embraced the Germans, included them in the legitimate history of Europe, and he asserted very convincingly, even those who don't accept his thesis actually accept the framework of thinking, that the decline of the Mediterranean started when the Mediterranean was divided between the Muslims in the south and the east, and the remains of Rome in the north. When we examine what happens in Palestine, in Israel, in Palestine, and elsewhere, according to recent archaeological excavations, we see again and again the same pattern. Cities in Israel and Palestine and countrysides continued to exist almost uninterruptedly during the Muslim period. And if you look at Jerusalem, this is Jerusalem of the beginning of the 8th century, the Islamic Jerusalem, all the excavations that were held in Jerusalem in the last 20 years or so show that Jerusalem continued to be almost as big as it was in the Byzantine period, declining abruptly in a later period, in the 10th and 11th century. These are the results, for example, of this is the reconstruction of early Islamic Jerusalem. And that was held along the road number 1 and the light train. You can see that according to all the archaeological excavations, early Islamic Jerusalem was almost as big as it was in the Byzantine period. It was different, but it was a big city. I will just mention briefly Ramle, for example. The city of Ramle in the early 11th century was 10 times bigger than the city of the Crusades. 10 times bigger. Tiberias. City of Tiberias, I'm sorry for the Hebrew. The city of Tiberias was 3 times bigger in the early Muslim period, longer. 3 times longer in the early Muslim period than it was during the Byzantine period. The city of Ramle, the city of Tiberias, and Jerusalem, we can show even in Israel, not in Iran, not in Iraq, not in Fustat, not in Baghdad, we can see a sudden and unexplained decline, collapse, that can be dated almost accurately to the period between 1055 to 1063. In Jerusalem, all the excavations made in the Umayyad palaces and south of them revealed that all this area was inhabited until 1033. In Tiberias, in Ramla, and elsewhere, this is Tveria as it was in the late 19th century, but in all the archaeological excavations showed something very strange. A huge number of hoards of treasures that were hidden in the buildings. All those hoards discovered, like this one in Tiberias, were dated to the 1060s, 1050s. Not less than 30 hoards were discovered archaeologically in the last 20 years, all over the country. All of them from the same period. Usually, archaeologists explain such hoards by the advance of enemies, people hiding their treasures for the fear of the enemy. I don't accept this explanation. When the enemy is in the gate of the city, you don't hide your treasures. You take whatever you can and run away. The chances to come back are very slim. You hide your valuables, or you are forced to leave temporarily, and you are afraid of what will be in the roads, to look for a sack of wheat, to look for food for your children or for your family. You hope to come back. We have a beautiful text written by Ibn al-Sirfi about one of the viziers of Kafur in the 960s. One of his viziers was a renegade Jew, a Jew who converted to Islam, and he rose to power because he was able to tell Kafur, the great vizier, about hoards that were hidden by Jews in Ramle and Farma, by Jews who left their dwellings and never came back because they disappeared in the roads because of the hunger, because of pestilence, because of things like that. I can continue telling about what this is another hoard, a beautiful one of the most beautiful ever found in Caesarea, again from the same period. I'll give you, because those who spoke before me and Nir, who is going to speak after me, are scientists, I have to show some numbers in order to be considered serious, not humanities. So I'll give one graph and two charts. When I speak about a very long and very strong series of droughts in the Nile Valley, I refer to such a list, for example. Before the 9th century, between the 4th and the 9th century, we know about 9 events of droughts in the Nile. That 9 events of 11 years altogether in 650 years. And as I told you before, droughts in the Nile are something that it is either there is a famine in the Nile or not. The Nile obtains its water not from the rain in the Mediterranean, but from East Africa, from the monsoons of East Africa. In September, in the Coptic New Year, which is also the Jewish New Year, approximately, the Nile rises. If it rises enough, there is enough water to water the delta of the Nile and to produce food. The rise which is considered sufficient and good is a rise of about 8 meters. If the Nile rises to less than 8 meters, 16 cubits, and you can see the installation, the Nilometer, that was constructed to measure exactly the yearly rise of the Nile. If the Nile rises up to 16 cubits, there will be enough food. If it rises to 15, there will be drought. If less than 15, disaster. As simple as that. If more than 16, plenitude, abundance, happiness, whatever. So it's either above 16 or below 16. And we know, because Egypt is the mother of bureaucracies, everything is written, everything is mentioned, and everything is remembered. And before 950, there were only 11 years of drought in Egypt, about 1 year every 60 years. Let's see what happened between 950 and 1079. There were, again, 9 events in 120 years, but very long ones, lingering ones, disastrous ones. Look at the one between 963 and 969. 6 years long drought. Between 1023 and 1026, 3 years long. 1052, 1056, 4 years. And the great calamity that led to the destruction of Fustat, 1065 to 1072. Biblical drought of 7 years. I made calculations that I'm not going to show here about how many years of plenitude are needed to provide for 1 year of hunger. In the Bible it is simple, 1 for 1, but it is not true. You need more. And a big amount, such a big amount of lingering droughts were causing destruction and hunger, because the bureaucracy was not able to hold enough food for the famine. So you can see that there were 27 years in 122, almost 1 year of drought every 5 years, whereas earlier in the better period it was 1 year of drought every 60 years, which is something a bureaucracy can handle. So I just give you. I have hundreds of texts describing this lingering disaster. Just some examples. This one was taken from Sibit Ibn Jawzi, describing the year 1027. In the year 1027, continuously from November to January, came a cold that no one had ever known before. Water froze solid throughout this period, including the shores of the Tigris and the White Canal. Browse also is telling about such things, and again, we have hundreds of texts. I will give you just, I promise you a graph. This graph was not made by myself. It was made by Kostas Kaplanis. I guess Kostas Kaplan is something that the debasement in an article called "The Debasement of the Dollar of the Middle Ages." Dollar of the Middle Ages is the gold coin of the Byzantines. that was stable since it was first, I mean, for many hundreds of years. It was stable. But the arrival of the nomads between 1027 and 1071, when the Byzantine Empire was defeated once again in the Battle of Manzikert, within 50 years, we can see that the gold coin was debased by 27%, both of them. The bigger one, the nomisma, and the tetrateron, the smaller one. So we can see the amount of knowledge, the amount of text, and amount of evidence. And I didn't enter the scientific evidence taken from course in Iceland or from Mongolia, because I think that the signals that history and archaeology can show are much more accurate and much better located than scientific. But everything shows that the collapse or the real end or the real collapse of classical antiquity in our region should not be linked to what happened in Rome, which was also decimated during this period, but this is a different story, not linked to what happened in Europe. The way we read history is very Eurocentric. We believe that what happened from Rome to the north is the beginning of the medieval or not. But I think there is a hint here to see what was seen by many scholars in the past, that many elements of classical learning, writing, continue to exist in the Eastern Mediterranean between the collapse of Rome and the 11th century. Actually, when we speak about the 11th century, this part of the world was the most literate part west of China. People were written here in the Eastern Mediterranean in many languages. In order to prepare what I was showing you this afternoon, I consulted books that were written originally, not all the languages I can read myself, in, I think, dozens of languages. Coptic, Armenian, Syriac, Arabic, Hebrew, the Gniza, Persian, and so on and so forth. Learning continued to exist in the Eastern Mediterranean, the Golden Age of Baghdad, the Golden Age in Kairouan, and in Egypt, until the 11th century. It did not stop afterwards. It changed direction. It had to be born again. But for us historians who were brought on the idea that everything is a process, everything is something that should be read in context of very long history, it is very difficult to see something like that. That in a short period of time, in many cultures, something happened that changed the normal behavior of those cultures. Thank you.
Thank you. Thank you, Professor Ellenblum. If it was this time, if we had our current time, they would say it's the opposite of global warming and there'd be a whole lot of issues. But this shows how history does have its variations. So thank you very much for that most interesting talk. Our next speaker is Nir Shaviv. Now we're going back to our physics theme. So Nir Shaviv has, his education includes a Bachelor of Arts, summa cum laude from Haifa, Master of Science in Physics, also from the Technion, and his PhD is from the Technion. He did, part of his postdoctoral work was done at the Canadian Institute for Theoretical Astrophysics in Toronto, and he was also at Caltech, and he's done teaching at the Technion, and now he's back at Hebrew University in the Department of Physics. So, Nir Shaviv.
I'm going to switch gears a little bit and talk about something different related to what some think is our doom, but it isn't. Let me just change the laptop quickly. Okay, I'm going to talk about global warming, but I'm going to talk with a different perspective. I'm going to try to convince you that the story that we hear every day in the media is, well, slightly exaggerated. And in fact, we should tend to other more urgent matters than thinking about what will happen in, say, 100 years. Okay, I'll start with a standard picture, try to to set the stage. We have the greenhouse effect. What the greenhouse effect does is the following. We have Earth in equilibrium. Suppose we didn't have an atmosphere, we would get some shortwave radiation from, do you have a pointer here? No. We have some shortwave radiation coming from the sun. Some of it is reflected back into space, but some of it is absorbed in a surface and then re-emitted. Now, in equilibrium, Earth doesn't heat or doesn't cool. It basically has to re-emit whatever is absorbed by it, and we reach some equilibrium temperature. Now, if we have, for example, an atmosphere on Earth, what happens are several things. First, we have water vapor in the atmosphere. Water vapor blocks the radiation going out, and because it blocks the radiation going out, it's harder for the radiation for Earth to cool. So in order to cool at the same rate it heats by the sun, the temperature at the surface has to increase. In addition to that, we have clouds. If you have more water vapor in the atmosphere, we form clouds, and because of that, some of the radiation goes immediately into space. It's reflected, and it doesn't enter the system, and in fact, the clouds have a net cooling effect on Earth. Without any greenhouse effect, without the atmosphere, the temperature on Earth would have been -5 degrees, so globally average, whereas the water vapor heats by about 30 degrees, the clouds cool by about 10 degrees, so the average global temperature is plus 15 degrees, which is, of course, very close to the yearly average temperature in Jerusalem, which is not surprising given that Jerusalem is the center of the world. Now, if we add CO2 to the atmosphere, what we do, we block some of the outgoing infrared radiation. It's harder for Earth to cool, and as a result, the temperature at the surface has to further increase in order to emit or to lose the extra radiation that we get. An interesting anecdote: greenhouses don't heat because of the greenhouse effect. Greenhouses heat because they block the motion of the air and something called convection. Anyway, this is the standard story that we are being told. If you open the IPCC report, the interpanel, the UN's interpanel for climate change. Sorry, it's a Freudian slip. That's what you'll see. You'll see that over the past thousands of years, thanks Tsvi. over the past thousands of years, we see that the temperature has, sorry, not the temperature, the amount of CO2 in the atmosphere has increased. But over the last 100 years, or a little bit more, from the time of the Industrial Revolution, we see that the amount of CO2 in the Earth's atmosphere simply skyrocketed. And we know that this is attributed to human activity because we can look at the composition of this CO2 and see that it's because of the burning of fossil fuels. Now, we see a change in the atmospheric composition, and at the same time, we see that the temperature on Earth has increased over the past century. The seas have increased their level, and we see less snow on Earth. So we're being told that this is the cause, and this is the effect. Case closed. We can even simulate it. We can put in all the physics into complicated computer models. Then start simulating, and we see that, for example, over the next 100 years, if we continue to increase the amount of anthropogenic greenhouse gases in the atmosphere, we're going to hit the global temperature by something like 3, 4, or 5 degrees Celsius. Even more if you're measuring in Fahrenheit. But it's the same. Okay, so basically this is what we're doing to Earth. It's not very pleasant, and we should therefore stop doing it. Okay, this is a standard picture, which I'm sure you're all aware of because you have been hearing it every other day in the media for the past a decade or more. But there are problems in this picture, and I want to, I'm sorry, I'll have to get a little bit technical in that, but I'll try to show you that the story is much more complicated and in fact doesn't hold a lot of water. I have to get technical because if I just bring you the claims, you might think, oh, he's a crackpot, he's swimming against the rest of the scientific establishment, but this is not the case. Okay, now, what are the problems with the CO2? First, there is no fingerprint that proves that warming over the 20th century is because of CO2. In fact, if you look carefully, there is no single period in Earth's history during which there were changes in the CO2, and as a response, there were changes in the temperature. There are none. You cannot show empirically that CO2 increases the temperature or that it has a large effect on the temperature. Now, some of you might have seen this movie, this science fiction movie by Al Gore. And in this movie, you have seen the following graph. There was a temperature reconstruction and the CO2 reconstruction based on ice cores, this one from Antarctica. And what you see is that, or what Al Gore says in his deep voice, because he wants to sound authoritative, he says, when there is more CO2 in the atmosphere, there is a higher temperature. The temperature is higher. He wants us to think that CO2 causes a higher temperature. But there's a correlation problem here. Or more specifically, a chicken or the egg problem. Is it the CO2 which is driving the temperature, or is it the temperature which is driving the CO2? And in fact, in all cases where you have ice cores with a high enough resolution, which is not the case in the ice core that Al Gore has shown us, you see that it is CO2 which is lagging behind the temperature by several hundreds of years. Namely, we can say for certain that temperature affects the CO2, but we cannot say anything like that about the effects that CO2 has on the temperature from this graph. There should be an effect, but this graph doesn't tell us what this effect is. The reason that the temperature affects the CO2 is because the CO2 has an equilibrium between being in the air and being dissolved in the oceans, and this equilibrium is temperature dependent. It's like the CO2 in your Coke bottle. If you forget it in your car, what will happen to it? If you open the Coke bottle, it will explode in your face, and the reason is that when you heat the Coke or when you heat the oceans, you change the equilibrium such that there is more CO2 in the air or in the atmosphere. Okay? If you look on longer timescales, on geological timescales, you can reconstruct the temperature, and this is temperature reconstructed using oxygen isotope ratios in brachiopods over the past 500 million years. And you can also reconstruct the amount of CO2 that there was in the atmosphere during the same period. And you see that there is no correlation. And the fact that there is no correlation can be used to place an upper limit on the effect of CO2 on the Earth's atmosphere. And this upper limit is an increase of 1.5 degrees Celsius if you double the amount of CO2. Just for comparison, the IPCC tells us that the temperature increase following CO2 doubling is anywhere between 1.5 degrees and almost 5 degrees, and all the doomsday scenarios are based on 3, 4, or 5 degree increase per CO2 doubling. For example, 450 million years ago, there was 10 times as much CO2 in the Earth's atmosphere as there is today. Mind you, this is a logarithmic scale. At the same time, there were glaciations which were as extensive or even more extensive than you have today. Basically, CO2 doesn't have a large effect on the temperature. There are other problems with the CO2. We are being told that we can explain the observed, here in red, the observed temperature increase over the past 100 years using computer models, which are here given in gray. And they tell us, you see, our models are good. We can explain the temperature increase. But what they don't tell you, or they don't emphasize, is the fact that there is a large uncertainty in these models. What you see here, this is a graph taken from the draft of the IPCC's 4th assessment report. It's in the draft and not in the final version because it's too embarrassing. Now, what does this graph tell you? It tells you what is the probability that we, for example, cause the heating over the 20th century, or even a cooling over the 20th century. With a finite probability, we may even have had a net cooling effect on the atmosphere. Basically, what it tells you is that we don't know what is the human contribution to the changed energy balance of Earth over the 20th century, and it basically means that we could have put anything into our models and we could have obtained a temperature increase which is larger than what was observed or smaller than what was observed. We could have obtained anything. The mathematician von Neumann said once that if you give him 4 parameters, he can fit an elephant, and if you give him the 5th one, he can wiggle its trunk. Okay, so this is what they're doing. Okay, more problems with the CO2. It turns out that there are problems with the details. Here you see the fits that we've seen before in the models in gray and the observed temperature in red. And what we see is that during the times of large volcanic eruptions, the models give us that the temperature should have decreased by quite a lot, while in fact the temperature on Earth almost didn't see any change in response to volcanoes. Now, why would volcanoes give you a temperature reduction? When you have a large volcanic eruption, you put a lot of dust in the stratosphere. This dust can stay there for a year or two. It blocks some of the sunlight, which is reflected back into space, and Earth should cool. And all the climate models which are used in order to explain the 20th century, they give you that the temperature decrease following large volcanic eruptions, like that of Krakatau or Pinatubo, should be somewhere between 0.3 and 0.5 degrees. In reality, if you look at what is the average temperature reduction following, say, the 6 largest volcanic eruptions, you see that it's a mere 0.1 degree. It's sitting somewhere in the noise. Basically, what it tells you is that all these climate models which are used to explain the 20th century global warming and which are used to explain or to predict the doomsday scenarios for the 21st century are hopelessly oversensitive. They give you a very large response which is not there. Earth is significantly more stable than what these climate models tell us. Now, why is the sensitivity not known? It turns out that model sensitivity in those climate models is not given by we don't know the physics behind it, and it's basically plugged into the models as a recipe. What do I mean? Suppose we heat the Earth, we change the energy balance. What will happen is that the temperature will start increasing. The temperature increase will evaporate more water vapor from the oceans. But water vapor, as I said in the beginning, is a greenhouse gas which wants to heat the Earth. So we will want to heat the Earth even more. This is a positive feedback. In addition, we are going to have more clouds in the atmosphere because we have more water vapor. But clouds have a negative, they have a cooling effect. It's a negative feedback. Now, it turns out that nobody knows if we change the energy budget or the temperature or the amount of water vapor in the atmosphere, nobody knows how to calculate what is the change in the cloud cover. And the change in the cloud cover in all these computer models is basically entered as a recipe. And because it's entered as a recipe, different recipes give you different climate sensitivities. I can take any computer model, change the recipes, and get whatever sensitivity you want. Okay? More problems with the standard picture that we hear. The CO2 or the anthropogenic warming that we get from the computer models, it turns out doesn't only tell us what the average temperature increase is going to be, it also gives us a geographic distribution. What we see from the computer models is that the heating should be all along the atmosphere. It should be in equatorial regions more than in northern and southern latitudes, and it should be all the way up to about 15 kilometers, and at high altitudes more than at low altitudes. Okay? If there is a fingerprint or a possibility to do fingerprinting of the warming, this should be it. But what is the actual heating that we have seen over the past 30 years? Using radiosonde data, using balloons, what you see is that the heating over the equator is smaller than the heating that you see in the subtropics. And in fact, what you don't see here is that the surface warmed by twice as much as the rest of the atmosphere, which is totally inconsistent with what the anthropogenic greenhouse gas models predict. So if you had a fingerprint, this should have been it, but it in fact points to something else. Okay, so how can we blame humans for the warming? What is the reasoning that we can do so? It turns out that the two arguments are very circumstantial. One is that we see warming, we cannot explain the warming with any other cause, so it must be CO2. The other argument is that the warming observed over the last century is significantly faster. It's not the same as the temperature or the behavior that we have seen over the past millennium. If you would Google ClimateGate, you would see that this graph that the IPCC based its argument, this hockey stick graph, is nothing else but a charade. What you see here, actually a better term would be shatnez. Anybody here knows what shatnez is? You don't have to explain. It's okay. Anyway, it is a shatnez, and what do I mean by that? What you see here, this is a temperature reconstruction using tree rings, and you see that the temperature almost didn't change over the past millennium, and then it started changing over the 20th century, but after 1961, the reconstruction didn't show any further temperature increase, which is strange. So what did they do? They just cut the data beyond 1961, and they stitched thermometer-based temperature measurements. So this is really a shatnez. And when you do this stitching, you get something which looks like the hockey stick. It's in fact very interesting. If you would have opened the first IPCC report, you would have seen that it was well known that Earth has had a varying climate. For example, in the Middle Ages, not the early Middle Ages, which Professor Ellenblum just talked about, which was actually, there was a short cold period. The Middle Ages, or the later Middle Ages, were much warmer. You could have Vikings circle Greenland and call it Greenland because there was no ice there in the summer, or there was a little ice age. There was a variable climate. Then one day, like the people in George Orwell's 1984, people woke up in the morning and voila, history has changed. Anyway, we know that this is correct. There are temperature variations, and the temperature increase over the 20th century is in fact not unique, and it's not unprecedented. So is there other explanation to the temperature warming? And it turns out that there is. and this explanation is that of the sun. We know that the sun is a variable star. It changes its activity. This is what the sun looks in soft or in UV between when it's inactive and when it's active. And because of this, this changed activity in the sun, which is associated with sunspots and solar wind and the amount of X-rays and the amount of UV that the sun emits and things like that, this changed activity, turns out, has an effect on Earth's climate. Now, the first one to suggest that there is such an effect is Sir William Herschel. He did that in the 18th century. He didn't have any good climate indicator, so he looked at the price of wheat in the London wheat exchange under the assumption that climate will affect the price of wheat. And he said that there's a correlation with sunspot number in a somewhat opaque paper, which I tried reading, and it was, well, opaque. Anyway, 200 years later, Eddy realized that climate over the past millennium, as can be, for example, seen here in the severity of winters in Europe, correlated with solar activity. For example, the Little Ice Age in Europe corresponded to what's called the Maunder minimum, during which there were almost no sunspots on the Earth, on the sun. Today we have other indicators. For example, you can look at what the temperature variations on Earth are with the solar cycle, and you see that there are peak-to-peak variations about 0.1 degree Celsius between when the sun is at solar minimum and when the sun is at solar maximum. I think I forgot to mention that solar activity has a cycle, or almost a cycle of 11 years, and on this cycle there are long-term variations which modulate this cycle. So you can see that in the oceans, or you can see that in the land temperatures. On longer time scales, you can see here carbon-14 from tree rings is a proxy for solar activity, and you can see that it correlates very nicely with a climate proxy, and this is oxygen 18 to oxygen 16 isotope ratios in stalagmites in a cave in Oman, which is an indicator for the temperature of the Indian Ocean in this case. Why? It's a little technical, and if you want, ask me at the end. You can see a similar thing in the Arctic climates. Here you have carbon-14, which again is a proxy for solar activity in blue, and in black you have sedimentation records from ocean cores. Basically, when it's colder, you get ice carrying its dust further south, and when the ice melts, this dust settles at lower latitudes. And here you see a correlation between solar activity and the Arctic climate. You can also see that in Israel, at least statistically, in the annual layers in the Dead Sea sedimentation bed, it's not as nice or as clear as the previous two examples, but it just shows you that even the climate in Israel changes because of solar activity. Okay, now what's the origin of this link? Now we know where this link comes from. In fact, it's related to the supernovae that we heard at the first talk. It turns out that when you have such a large supernovae and the expulsion of this envelope, of the stellar envelope at high speeds, these envelopes hit the interstellar medium and accelerate particles to very high energies. These particles roam, they later roam the Milky Way, they diffuse along the Milky Way, and some of them can reach the solar system. Now, what happens to these particles in the solar system? When they reach the solar system, they meet the solar winds. The sun, as I mentioned before, has a solar wind, which changes due to the solar activity. Here we see the solar wind. This is the solar disk. We see here a comet which fell into the sun. It's like Icarus. It flew too close to the sun, so it melted and didn't come out from the other side. Comets have tails because of the solar winds. When these particles from the solar wind reach the Earth, are funneled along the magnetic field, they hit the atmosphere, and we see them as aurorae in northern and southern magnetic latitudes. Now, the solar wind is very interesting because it changes the flux of this high energy cosmic rays which reaches the Earth. Now, why does it do that? The solar wind blows a bubble around the solar system, just like this flow from the faucet blows a hole with a very fast moving fluid and a shock wave. This thing, which is called the hydraulic jump, is a shock wave, and it's exactly the same as what we have here around the sun. So what happens? These high energy particles, they roam the Milky Way, they diffuse around the Milky Way. Those that reach the solar system, they have to penetrate the solar wind and they lose energy. So when the sun is more active and it has a stronger solar wind, less of these particles reach the Earth and we get less ionization. It turns out that the amount of ions that we have in the lower part of the atmosphere is basically governed by these cosmic rays, these high energy particles, which on average accelerated from supernovae 20 million years ago. Nowadays, we know, this is, here you can see what these cosmic rays look like. There are experiments even showing you how when you change the amount of ionization in the atmosphere, you change the growth of cloud condensation nuclei. And there is now a theoretical picture which basically tells us how when you increase the amount of ionization, you change the growth of condensation nuclei. And, okay, it just tells me that the time is done. When you change the amount of condensation nuclei, you change the characteristics of the clouds. Here you had ships pass by, burn dirty fuel, and the exhaust served as cloud condensation nuclei, and we changed the parameters or the characteristics of the clouds. So what we know the link is today, we know that changing solar activity changes the solar wind, which modulates the flux of these high energy particles, changing the ionization of the atmosphere and controlling the cloud cover. We can see that empirically with a changed cloud cover together with the cosmic ray flux reaching the Earth. Since we have to be short because we started late, I'm going to jump over the rest of the evidence that shows you that cosmic rays affect climate. The only thing I want to tell you is the following. We know now that cosmic rays affect the climate, and therefore also the sun affects the climate, because over the 20th century, solar activity has increased. Solar activity has increased over the 20th century. We get less cosmic rays and less cloud cover, and this should cause some warming. How much warming? We can estimate it at between half to 2/3 of the warming over the 20th century as attributable to the increased solar activity. What does it tell us about the 21st century? We can also use standard IPCC models to predict what the increase over the 21st century is going to be. And what we find is that the temperature increase should be somewhere between 0.5 degree to 2 degrees. And this is comparable to the 2 to, say, 6 degrees that the IPCC frightens us with. And I think that I will summarize with this quotation. I'll quote Al Gore quoting Mark Twain, who said, "What gets us into trouble is not what we know, it's not what we don't know, it's what we know for sure that just ain't so."
Thank you. I'm going to save questions till the end. So we're going to finish with a little time so everybody can get questions, but we've got to be fair to everybody. So we're going to continue. But I want to get some chance for questions. So thank you, Professor Shaviv. That was very interesting. And many of us have thought that there's some histrionics going along with this global change. So we need the physicists to prove it. And our final speaker is Bianca Kuehnel. Hopefully I pronounced that properly. Now we're going to shift gears. Professor Kuehnel got her BA from Hebrew University, MA from Hebrew University, and PhD from Hebrew University. She is presently the Jack Cotton Professor of Architecture in Fine Arts in the Department of History of Art at Hebrew University. She's also the Director of the European Forum at the Hebrew University. Her background includes having spent time at Free University of Berlin, the National Art Gallery in Washington, D.C., and at the Max Planck Institute. And recently, she's just received a 1.8 million euro grant from the ERC, which is a very prominent grant. So with that, Professor Kuehnel.
Thank you very much. Thank you. Well, for thus thou art, and unto thus shalt thou return, seemed to me too final a sentence to let you take it with at the end of this board meeting. So this presentation is dedicated to what comes after. The preoccupation with what comes after death is a constant of the human mind and an integral part of various human civilizations and cultures. One can safely say that the preoccupation with death and afterlife played a decisive role in the formation of Western civilization out of a crucial confrontation between pagan, Jewish, and Christian beliefs at the beginning of our era. The first encounters and exchanges took place in cemeteries at a time when monotheistic religions were barely tolerated, and the promise of afterlife was definitely a means of escaping the gloomy reality of declining economic and social conditions accompanying the gradual fall of an empire that stretched its domination beyond any limit, the Roman Empire. Eschatology, the belief in afterlife, shaped the visual imagery of funerary art. Even pagan art turns during this period toward eschatological motives. The innocent-looking peacocks flanking a bowl of fruit are symbols of paradise, while the reclining lady in a summer landscape, in fact a personification of summer, stays for the immanent passing of time, conceived in itself a guarantee to the inevitability of the continuation of life after death. Figures such the orans, which is the personification of prayer, the philosopher, and the good shepherd, that decorate the walls of catacombs and facades of sarcophagi are meant to ease the pains, the uncertainties, and the fears inspired by death. Promises of redemption were at the core of several other beliefs, alternative to polytheism, which flourished during late antiquity, each being centered around a hero god who, through his own deeds, provided guarantee of afterlife. Mithras, Zoroaster, Dionysos, and the most successful of all, Christ. Christianity, the religion adopted by the Roman Emperor Constantine, offers a coherent program of human salvation made possible by Christ's sacrifice, the crucifixion. The promise of the future salvation of souls is built on Christ's life, death, and resurrection, and argued for theologically and visually, either with the aid of miracles performed by Christ himself or with typological exempla from the Bible. Christian funerary art being essentially paradigmatic. Daniel's salvation from the lion's den and the miracle of Lazarus' resurrection belong to the standard repertoire of both catacomb painting and sarcophagi reliefs. Following the upgrading of Christianity to a state religion after Constantine the Great, visual imagery becomes bolder, expressing the claim to universality through monumental depictions of Christ's majesty, in heaven as judge, as in the Santa Pudenziana from the 5th century in Rome, presiding over the tribunal of apostles, or in his second coming, descending on clouds at the end of days, again in Rome, 6th century. I am dealing for many, many years with various aspects of Christian art and iconography, and if you would ask me to summarize in a few words Christian art and iconography, I would say that its most salient characteristic is the claim to universality. This aspect fits extremely well in this year's board framework without the slightest need to force it in. Origins of the universe and humankind. Christian art gives shape to the Christian claim to universality by illustrating its claim on creation and on history of the humankind ever since, on the rules and secrets of the universe as premises to mastering the final scenario at the end of days. The visualization of the universal order of things makes ample use of science. Scientific precision confers theological images authority and credibility. The creation of the world with the aid of a compass turns a biblical story into a fact, and the creator, depicted as Christ, into an engineer that has carefully planned the world and is faithfully executing his plans. The element of planning in creation is extremely important since it meant to contain the outcome of creation as well, namely salvation, or more precisely, is meant to argue and justify the belief in the immanence of salvation. The ultimate instrument of salvation is the cross. It is through his suffering and death on the cross that Christ liberated humanity from the original sin of Adam and Eve, thus making salvation possible. This is why Adam and Eve feature permanently in Christian funerary art. The very shape of the cross, while evoking the sacrifice, is ideally made to visualize the universality of its own message. In a 9th century manuscript of Beda's treatise on nature, the cross appears to be holding the diagram of the 12 winds. The cardinal directions are inscribed within the flared ends of a cross that protrude behind the diagram disc. The identity between the cardinal directions and the cross encompassing the whole world is thus made visible beyond doubt. In some Mappe Mundi, the crucified himself is shown holding the world in a similar, although more elaborate and explicit way. As here in the 12th century Epsdorf map, you can see Christ's head, hands, and feet to indicate his body stretched over the cross. The symbiosis between scientific knowledge and biblical exegesis is so strong that it works both ways, in biblical iconography and in scientific diagrams. Isidore of Sevilla's treatise on nature, from the beginning of the 7th century, the backbone of medieval physical science, the channel and filter through which ancient science was transmitted to the Middle Ages, contains 6 circular diagrams composed by Isidore himself that show in the numerous medieval copies the same compositional principle. They make visible the concordance of many interrelated physical data with the shape of the cross resulting from their arrangement. Folio 11 of a copy of Isidore's treatise on nature in Munich shows a diagram which is representative for quite a large group of similar Carolingian manuscripts. The circle of the year is usually inscribed with the word annus at the center of the diagram. The 4 seasons, accompanied by the corresponding cardinal directions, are placed opposite each other. Spring, ver, is equated with oriens, because then all things arise, oriuntur, from the earth. This pair of terms is placed above the central inscription annus. Autumnus, autumn, is associated with occidens because of serious illnesses and because the leaves fall from the trees. Occidus meaning setting or falling, both placed at the opposite end under the central inscription. Summer, aestas, with south, meridius, are on the right, both having heat in common, whereas winter, hiems, with the north, septentrio, connected by cold, are placed opposite on the left. Each season is characterized by its primary qualities: dryness and humidity, heat and cold, inscribed in between. Since these qualities are shared by the seasons taken 2 by 2, they serve as natural bonds or common elements, uniting them. The seasons, tempora, thus derive their name from the balance, temperamentum, of their common qualities, as time, tempus, derives its name from the same balance between contrasting forces of nature. The figure communicates this message of balance by the intertwining of a set of 8 half-circles with a common base, the circumference of the rota, of the circle. Each half-circle comprises a season, a cardinal point, and their 2 qualities. Spring is humid and hot. Autumn is dry and cold. Summer is dry and hot. Winter is humid and cold. The system of 8 intertwining half-circles also demonstrates that each quality is shared by 2 seasons. Humidity is divided between winter and spring, dryness between summer and autumn, heat between spring and summer, and coldness between autumn and winter. The diagram provides a simple but sophisticated way to express unity in diversity and balance, the symmetry of the colors adding to the quality and to the clarity and stability emanating from the diagram. To the year, the seasons and their qualities, the 5th scheme adds mundus, the world, and homo at the center, and introduces the 4 elements, ignis, aqua, terra, air, and the 4 humors, red bile, blood, phlegm, and black bile. Usually these rota, these circles, are centered around the triple inscription mundus, annus, homo, as for example in the same manuscript from Munich at another folio. The association of these data in one diagram is meant to illustrate a concept of ancient origin that became popular during the Middle Ages, namely that man is a small world and the world a great man. The emphasis on 4 axial directions create the shape of a cross with flaring arms that dominates the whole figure, a common feature of all manuscripts containing the 2nd and the 5th Isidorian diagrams. A large number of direct representations of the cross displaying the same layout of crosses and circles, for example, this Irish monumental cemetery cross in Clonmacnoise from the 9th or 10th century, shows a striking similarity to our diagrams, thus documenting the link. An explanation for this similarity is found in the Theology of the Cross, a major part of which is devoted to defining the cross's role in supporting the architecture of the world and preventing its components from falling apart. The Fathers of the Church stress the paradox of the cross's apparent lack of power and its being simultaneously the inner, invisible structure of the world, the eternal, predetermined plan of the universe. A 5th century epistle by Isidore of Pelusium that sums up the early Christian position regarding the cosmological role played by the cross is especially evocative of the diagram of the elements discussed above. Quote, The glorious cross is rightly named the backbone and jewel not only of the earth, but also of heaven. It is indeed the source of the entire creation, the author of heavenly joy and earthly liberation, and the cause of the union between opposites. John of Damascus provides a link between early Christian and medieval exegesis on this issue of the theology and adoration of the cross, summing up its main lines toward the middle of the 8th century. The visible arms of the cross springing from a center point towards the godly power of the Logos on the cross that radiates vertically and horizontally to hold together the visible and the invisible creation. This theological concept is clearly visualized in the harmonious interplay of the elements and qualities in our diagrams. The union between diagram and cross becomes one of the most direct visual expressions of a line of thought which is basic to Christian exegesis, namely that Christ, through the crucifixion and resurrection, which make him the meeting point between death and life, halted in himself the decomposition of nature caused by death, and thereby exemplified the principle of the reunion of scattered elements. But there is more to it. We shall try to search for a deeper meaning of the association between diagram and cross, between science and exegesis in Christian art, with the help of a sophisticated and explicit visual example. The manuscript, this 9th century manuscript in the Vatican Library, is a scientific computistical miscellany dated to the Carolingian period. A wind diagram located on folio 66 shows a seated figure of Adam in the center, surrounded by animals, a scene easy to recognize as Adam giving names to the animals, according to Genesis 2:19. Personifications of the 12 winds identified by inscriptions surround the Adam Clipeus symmetrically, their feet emerging from clouds arranged in such a way as to constitute an additional external circle. The personifications address themselves to the central image with the turn of their bodies and the direction of their heads, hands, and trumpets. While all the personifications blow a trumpet, the cardinal winds and the cardinal points are further distinguished by their wings. The association of the vocatio animalium, rarely depicted in medieval art, with the 12 winds in a circle of a computistical manuscript is unique, as is also the emblematic depiction of the Genesis scene. Adam is seated frontally and majestically on a rock, clad in an imperial mantle with a fibula, his long hair falling evenly on his shoulders, hands open in benediction and acceptance. He is flanked by 2 trees in the upper part of the medallion, and docile birds and animals in the lower part. The composition recalls early Christian catacomb depictions of the Good Shepherd or of Orpheus, as for example the Orpheus, the Christ Orpheus from a catacomb in Rome. The association between Adam and the winds, especially in a representation that emphasizes the 4 cardinal winds by giving them wings, evidently refers to St. Augustine's treatise on the Gospel of John. There, Augustine speaks of Adam forever spread throughout the world, since if one takes the first letters of the Greek names for the 4 parts of the world, that is the whole world, one obtains the name Adam, Anatole, Disis, Arctos, Mesembria, east, west, north, and south. We know that Augustine's works were much loved by Charlemagne, who had extracts read aloud at court after dinner. In his commentary on the Psalms, Augustine establishes a connection between the apocalyptic vision of Christ gathering his elected from the 4 winds with a great sound of a trumpet, according to Matthew, and Adam, who is spread throughout the world according to the Greek alphabet. Christ will gather the pieces from all over the world and fuse them in the fire of love, thus bringing together what has been broken apart. The trumpets and the transformation of 4 of the winds into angels in this extraordinary miniature evoke an additional association with Revelation 7. 4 angels stand at the 4 corners of the world, holding the 4 winds, so that the angel who comes from the east can seal the just before the beginning of the end. Adam's act of giving names to the animals is thus parallel to the sealing of the just before the judgment. The identity between Adam and Christ in effect reflects the equation between salvation and creation, which is a locus communis in Christian exegesis, both Eastern and Western, and in Christian art. One of the earliest sources of this line of thought seems to be a sentence in Paul's epistle to the Ephesians, speaking of the recapitulation of all things in Christ. The notion of recapitulation has engaged exegetes from Irenaeus until the modern period. The recapitulation doctrine considers the virgin birth of Christ as the first sign given by God of the salvation he intends to operate. This miraculous nativity is paralleled with Adam's birth from the virgin land, to emphasize the idea that recapitulation is by no means new creation. The first Adam contained all men to come. The second Adam recapitulates all peoples, all languages, and Adam himself. The mystery of salvation is associated with the first creation, being conceived as the goal towards which creation was oriented from the very beginning. Christ is invested with the image and similitude of God that had been lost in Adam. This line of thinking can be, of course, be traced into the Carolingian period. In a titulus written to honor crosses and images of the cross in a church in Salzburg, Alcuin, the chief Carolingian theologian, sums up the cycle of sin and salvation and the parallel between Adam and Christ through the tree of paradise. Adam closed paradise to the touch of the tree, and through the tree of the cross, Christ opened Olympus. The meeting between this concept and the medieval theology of nature is witnessed by Eriugena, author of another treaty, Carolingian treaty on nature, from the 9th century. In his systematic formulation of the theory of return, Eriugena seeks arguments for the return theory in the sensibles of nature, meaning the heavenly sphere of the fixed stars, which is perpetually revolving and returns to its original position every 24 hours. Eriugena concludes that the natural laws governing the revolutions of the 2 great luminaries provide sufficient evidence of the doctrine being affirmed, the doctrine of return. Not only cyclical nature, but also the Christian concept of history is reflected in this theory of return. Man's fall leads to man's redemption, to return and unification, with God until creature and creator cannot be separated from each other. Redemption means man's return to his first life, to the angelic status which he deserted, and to the original status of his creation. Why, according to Eriugena, is the return necessary in the order of things? He answers, because all created things would be destroyed without a return. Since the created world contains the image of the deity, God would not permit his image to come to nothing. The return is operated by both nature and grace. Eriugena explains the need for the combination of these 2 factors when discussing the resurrection. In natural terms, the resurrection means the return of the 4 physical elements to the body from wherever they were scattered through death. But if the resurrection depended only upon nature, there would be no need for a Redeemer. And if the resurrection depended upon grace alone, the natural power and the vital motion of living things would be redundant. This concept concisely reflects the marriage between science and religion in Christian thought. A Huguenot's formulation also tells us why, when dealt with by Christians, the repeated phenomena of nature cannot simply amount to endless cycles. They must have an axis and a direction. In medieval thought and practice, nature is not an issue separated from history, since the same God created the natural world and freed it from historical sin through his Son. Christian time thus moves between the two superimposed poles of creation and salvation. I thank you very much for your attention.
Thank you, Dr. Kuehnel, for bringing it all together. So we have about 10 minutes left for some questions. So we first have our first question we're going to take from Canada. Go ahead. They're going to bring you a microphone so everyone can hear the question.
Yes. Professor Shaviv, two quick questions. Do you believe that there are any contributions to global warming that are man-related? And the second question is, and I say it with respect, are you considered by your colleagues as a kind of maverick, or do you have a group of colleagues that think alike and you are gathering a kind of consensus backing your views?
Short answer to your first question, yes. There is some contribution. Second question, the answer is yes. I'm not alone. There are many people who have been thinking like I do and for even longer. The thing is that what's interesting is that each one of us has been working in their own niche, where it be in astrophysics that I do, or in geology, or in other things, in paleoclimatology. And all of us have reached this conclusion, and yeah, so the bottom line is that I'm not alone. I don't think we are a majority in the scientific community, but science is not a matter of democracy.
Any other questions? If there are no other, you're allowed a second question if people don't have any other questions. Oh, yes, we do. Here.
One question for Professor Ellenblum. Do you think that the big schism between Catholics and the Greek Orthodox Church in 1054 on the Cerularius has anything to do with it?
Can you repeat the question and repeat it slowly and clearly?
Do you think that the big schism, schisma, but took place between the Catholic Church and the Greek Orthodox Church in 1053 had anything to do with this?
I don't think that anything that happened in the world in the 1050s is connected to what I was trying to show, including the Oman, the supernova, for example, that also happened at the same time. It's not closely related to what happened, really. I mean, seriously speaking, I don't know yet. I was asked about other things that should be considered along this event, like the history of the Crusades, in which I specialize. I think I would look first to what happened in Sicily, to the Normans. I think the history of the East Mediterranean in the 11th century should be reconsidered, but I don't have answers yet I have more questions than answers. Is it good enough?
Any further questions?
Sorry, I just came in because I had a phone call. I assume the question about global warming was, you know, how popular and whether it was, you know, a bit about. I'm going to ask another question about that, if that's okay. If what is causing the temperature rise, if it's not global warming, can you hear that? What is causing? And just before I'd like to make a comment that in the history of science, those who have challenged the gospel, you know, the truth, quote unquote, are in for a hard time. So I think you can expect to have a very difficult time with those people who believe that this is, you know, the truth. So I think you should be prepared for that.
Having difficult times is not a problem. It just makes life more interesting. And it's not that, I mean, it's not that in the future, it's already in the past that I've had, I don't know what, threats for lawsuits, for example, which, you know, is quite surprising in the scientific world. As for your first question, some of the warming, in particular if you look at the latter half of the 20th century, is because of humans, but it certainly doesn't explain most of the warming over the 20th century. And somewhere between half to 2/3 of the warming should be attributed to the fact that the sun became more active. And in fact, in the latter 50 years of the 20th century, the sun has been as active as it ever gets. The last time it was this active was perhaps 1,000 years ago during the late Middle Ages.
Any further questions? Yes, okay, go ahead.
Professor Shaviv, you claim that science is not a democracy. And I agree, it's a matter of evidence and a matter of proof. So, why aren't you a majority?
Why?
What makes most scientists disagree with you?
Money.
No comment.
There's another question.
I'll quote Al Gore again. I don't remember who said that originally. I don't know if it's related or not, but it's an interesting quote that Al Gore said in his movie. He said, it's hard to convince people of something when their salary depends on it, not understanding it.
We're going to need the microphone up to somebody up top.
Because of the potential consequences if you happen to be wrong on this issue, don't you think it sensible to take precautions just in case the majority of your peers are correct?
If the medicine that you need to take in order to treat an illness is worse than the illness itself, then perhaps you shouldn't take the medicine. And in this case, the illness is nothing more than a light cold. Now, the problem I see is that because of this issue of global warming, real environmental problems are not being addressed properly. And worse, in a few years, when people will understand that the temperature is not rising as fast as predicted in the climate, you know, with all the climate models or in the IPCC reports, people will do a 180-degree U-turn and will not believe any environmental issue should be addressed whatsoever. So I think it's going to be a boomerang. I think the environmental people are putting all their eggs in the wrong basket. Now, don't get me wrong. There are plenty of good reasons why we should burn less fossil fuels. I don't need to mention them, but things like they're depletable, they cause real pollution, which really kills people now and not in the future. It's controlled by sometimes not very nice governments, etc. So there are many good reasons why we should do so. And we should invest more in what Professor Piran, for example, mentioned in the beginning, in things like fusion technology, because if say 30 years down the road we'll have fusion, then all these things which we now quote unquote worry about will seem like as ridiculous as humans have worried about, say, passing the tail of Halley's Comet in 1910.
Thank you. We have time for one more question, if there is one. And if there isn't a question, I'm going to thank our speakers, Professor Tsvi Piran, Professor Ronnie Ellenblum, Professor Nir Shaviv, and Professor Bianca Kuehnel. And with that, we're going to close. This is the final panel, academic panel for the Board of Governors. So thank you all. And though, just to remember for those on the board, there's the last function at Mount Scopus this evening. Thank you very much.